Hello, this is the presentation for Chapter 2 of GD&T. In Chapter 2, we're going to talk about symbology on drawings, both the conventional symbology and geometric dimensioning and tolerancing symbology. So your objectives are identify and draw general dimensioning symbols and show their general applications. 2, identify and draw tolerancing symbols and show their general applications. 3, complete a feature control frame using the correct order of segments in the frame. And number 4, identify the basic dimensions and define means for indicating a basic dimension on a drawing or in a design model. Okay, let's start with our general dimensioning symbols. Some of these you have seen before. Okay, we have the diameter symbol, a counterbore symbol. The spot face symbol kind of looks like the counterbore, except it's got SF. There's the countersink symbol, an origin symbol, square, arc length. Here's a reference dimension. This symbol is used to define a slope. This symbol is used to define the depth, like the depth of a hole or a depth of a counterbore feature. And then this symbol is used as a conical taper. Now, let's talk about some definitions. Here's one that we're going to be talking about in this class a lot, which is called a feature of size. A regular feature of size would be a thickness or a width of a part or a length, an overall length of like a bar, for instance, or the diameter of a hole, or the outside diameter of a cylindrical feature. So feature of size. Symbol applications. Okay, so generally, most symbols will precede the value, which means that the symbol would become first and the value would come secondly. Symbols are preferred over abbreviations because symbols take up less space. Their abbreviations can be misinterpreted, so we like to use symbols. And then the symbol size is relative to the character height. And your textbook talks about the relative size of symbols relative to the text site. So let's look at our basic symbols for general dimensioning symbols. This would tell you what the symbol is, what a previous abbreviation would be in a note, and then what it actually means. So we got a diameter, a spherical diameter, kind of looks like the diameter symbol, but an S in front of it. We have a R, which is a radius, and a CR, which is a controlled radius. We'll talk about what that means later. SR is a spherical radius, and then these are the symbols we talked about before: counterbore, spot face, countersink. And we'll talk about these things as we progress in this class. Here's how to use a diameter symbol. Okay, on a drawing, the diameter symbol comes before the dimension, like this. And what we do is we'll put that between the dimensioning lines here. We have extension lines here and here from the diameter of the part, and then dimensioning lines are the ones with the arrowheads on it. Okay. Or the other way to do this is to look at the end view of the diameter and then point to it with the diameter symbol in front. In some cases, some companies like to dimension CAD models, and here's how that dimensioning would appear on a CAD model. Here's the symbol for a spherical diameter, like a ball hitch. Okay, and so what that means, that's a spherical diameter all over, kind of like a hitch ball, like I said. So the next one I want to talk about is the radius and controlled radius. Again, the symbol R appears before the dimension. Okay, this would be how it appears on a drawing, and this would be how it appears in a CAD model. Here is the symbol for a spherical radius and how it's applied. Okay, so it's not a full diameter, it's just a spherical radius. So we have SR and then dimension afterwards. Next one we're going to talk about is the counterbore. The counterbore and depth symbols. Okay, so what we're looking at here is a hole, a diameter 375, and that hole has a related feature. It is a counterbore. The diameter of the counterbore is 0.625, and the depth of that counterbore from the upper surface of the part is 0.25, quarter inch. Okay, that's how we dimension a counterbore. And by the way, that's what a counterbore is. It usually is used to recess the head of like a cap screw or something like that. So when you mount the cap screw, then the head of the cap screw sits below flush of the surface. The next one is the spot face symbol. Now the spot face is kind of like a counterbore, but it's generally used to clean up an irregular surface for a washer or a bolt head, for instance. So in this case, we have a diameter symbol, 375. We have the spot face symbol, diameter 0.625. And then instead of dimensioning the depth of the spot face, the thickness of the hole is dimensioned. Okay. And then typically that spot face, like I said, is to just provide a nice flat surface for which to seat a bolt head or a washer or something like that. Next one I'm going to talk about is the countersink symbol. Okay, in this case we have a 6 by. Okay, so what this X means here, the X means the number. So 6 by. That means we have 6 holes, and these holes are all diameter 0.281. And then here's our countersink symbol, and then this 0.438 is the diameter at which the countersink breaks out into the upper surface, and then 100 degrees is the included angle. So this is how we dimension a countersink using the proper symbology. Next one I want to talk about is a reference value. What is a reference value? So a reference dimension is enclosed in parentheses. And then the related symbols are also enclosed. If, say if it was a radius, that's a reference dimension, for instance. Okay, so in this particular case, we have a parentheses around this dimension here, the 1-inch dimension, because if we didn't call that a reference dimension, the part would be over-constrained. Now, what do I mean by over-constrained? Okay. So in this case, we have the 2.375 has a tolerance, the 0.750 has a tolerance, and the 0.625 has a tolerance. So in no way, shape, or form should we put dimensions on all 4 of these dimensions. We only put tolerances on 3 of the dimensions, and then this one here, the reference dimension, is allowed to be whatever the culmination of the other dimensions adds up to be. Okay, so if we didn't enclose that one in parentheses, we are committing a violation called double dimension. Okay, so let me finish this presentation here. The 1-inch dimension is redundant to the other 3 dimensions. The 1-inch enclosed in parentheses, which we made it reference by doing that, to prevent double dimensioning, which is bad practice. Okay, so that's why we use a reference dimension. The reference dimension is just shown to tell you what the nominal value is, but there's no dimensions associated with this. There's going to be a second presentation for Chapter 2, so I'll end this one here.